it has changed the temperatures from 20 degrees to 630 degrees, which happens to be its melting point. All right. So what are we looking for? We are looking for the specific heat of antimony. Well, if we get our equation here, which is Q equals MC delta T, change it to final temperature minus the initial temperature, our Q value there is what? 30.7 kilojoules. Our mass is 1 kilogram. Our specific heat, who knows? All right. Now our final temperature, 630, minus our initial temperature, which is 20. All right. Now, pulling out our calculator here, we are going to solve for the specific heat of antimony, and here's what we're getting. We're getting 30.7 divided by 1 divided by the quantity of 630 minus 20. So what does that mean? That means the specific heat of antimony equals 0.0503 kilojoules per kilogram degrees centigrade. Now, will the killies cancel? What do you think? Yes. Yeah, they sure will. All right, killi on the top, killi on the bottom. So 0.0503 joules per gram degrees centigrade. Now, why did I do that, and was I required to? No. Okay. This is just the unit that your book typically uses for this. All right. Remember, in a science classroom, you can use any unit you want as long as you write the units. Let me tell you what is traditional. If there is a problem written on a test, the professor expects you to use the units of the problem that he gives you unless otherwise asked. So for example, the professor says, well, how much energy is given here and there? And he gives you some energy in kilojoules. He expects that back in kilojoules unless he later says, please convert your answer to joules. All right? I mean, that's just common etiquette. Some professors mark off and are real anal retentive about that, and some ain't. All right? Me, if you got a unit that's right, good. All right? All right. So does anybody have any problems with that one? Okay, then number 26 says what? All right, if the late Brittany would come up here and work this for us. It said, no, I'm just carrying on. All right, here's what we got. A sample of metal with a mass of 250 grams. So this is just a random Jane metal. It's heated up to 130 degrees. Okay, so this is the mass of a metal. The final temperature of that is 130. Well, that's not the final temperature either. The metal's heated up to 130 degrees centigrade. Now, it is dropped into 425 grams of water, all right, at 26 degrees centigrade. The final temperature of the water, so that right there is the initial temperature of the water. The final temperature of the water is what? 38.4 degrees centigrade. What is the specific heat capacity of the metal if 1,200 joules was lost to the environment? So this is going to be 1,200 joules lost to the environment. Okay, so the problems we worked yesterday, it said, okay, all of the heat has been transferred from the water, from the metal to the water. But now it says it's not like that. The heat has been transferred from the metal to the water and outside the beaker. Okay, so how do we go about doing this? Well, this 130 here is the initial temperature of the metal. Now, what is the final temperature of the metal? The final temperature of the water, which is 38.4 degrees centigrade. Now, what is the specific heat of the metal? We don't know, right? And now what we're looking for? The random specific heat of the metal? Tell me all about water. Well, the mass of water is that. The specific heat of water is 4.184 joules per gram degree centigrade. Right? We got that out of the table. Initial temperature of water, final temperature of water, fine. So we're together, right? So what do we want to do? Do we want to use the same pattern as we did last time? Well, the heat of the water equals the mass of the water times specific heat of the water. Final temperature of the water minus initial temperature of the water. And the heat of the metal equals the mass of the metal, specific heat of the metal, final temperature of the metal, initial temperature of the metal. Oh, that's a subtract sign there. Okay, what have we got? The heat that leaves the metal is transferred into the heat of the water plus another 1,200 degrees, 1,200 joules. Right? That's right. The heat left the metal, yes, and it went to the water and out to the environment somewhere. Okay.
Not from the water, left from the metal.
Well, okay, I see what you're saying. The heat went from the metal to the water, then from the water out. Okay. But where did the heat originally come from? The metal. All right. So the heat originally came from here, so that's going to be the heat of the water and the heat to the surroundings. Will that work for us? Well, maybe, right? Who knows? Like I work these things. Okay, negative mass of the metal, 250. Specific heat of the metal, we don't know. Let's put an X there. Final temperature of the metal at 38.4 minus 130 equals heat of the water. Okay, here's what we got. 425 grams, 4.184. Final temperature of the water, 38.4 minus initial temperature is at 26. Yes? Plus what? 1,200. Right? Because see, now we've got another problem. We've got this heat leaving the environment. All right, so let's find our nifty-difty calculator and see what's happening here. Let's do the right-hand side first because it just happens to be easier. At 38.4 minus 26 times 4.184 times 425, enter, plus 1,200. So that's going to be what? 23249.68. Now that's good because I don't have any variables there on that side. All right. Now, negative 250 times the quantity of 38.4 minus 130 equals what? 22900x divide by 22900 divide by 22900. That means x equals 1.015. Is that what the back of the book's got? Yes? 1.02. Okay, fine. So we're together. Now, was there another part to that question? Or was that it, number 26? What's the specific heat? Boom. We're done. 1.02. Now, again, the idea is from yesterday that using a thermometer and a calorimeter, that one should be able to go up, get a table, and find out what type of metal it is. Okay? Are we ready to work more? 31? Is 31 going to be a problem? Yes? Wonderful. I like problems. So this is chapter 4, number 31 out of the textbook. Let's give it a read. It says 1 gram of anthracite coal. Okay. So first off, let's write down 1 gram of coal gives off 7,000 calories when burned. How many joules is this? So the first thing is let's just do this conversion here